All right, so coming back to part 2 of our What is Calculus video lessons, we're basically going to start looking at this idea of slopes because that's going to be a key concept where we're talking about our instantaneous rates of change. So first, let's talk about slope on a straight line. Very simple concept. Everybody learns it in Algebra 1. Pretty straightforward and easy to take care of. We want to find the slope at any and every point of the line passing through the point -2, 3, and 5, 6. So everybody, hopefully everybody in calculus knows that your slope formula, which is going to be your change in y over your change in x, your y2 minus y1 over your x2 minus x1, that we simply can plug and chug. We can take our 6 minus our 3, divide by our 5 minus our -2. Simply do a little arithmetic once we get to this point. Our 3 over 7, so we know that the slope between the points -2, 3 and 5, 6 is 3/7. But one thing to remember is that the idea, since I'm on a straight line, that the slope is constant. Slopes are constant everywhere on the line. Constant on the entire line. So if I were to ask for the slope at any and every point, I can simply use the fact that the slope of the line is 3/7 and know that the answer is going to be 3/7. If you were going to be asked what the average rate of change is, the average rate of change anywhere on the line is going to be 3/7. In a line, and only in a line, the average rate of change is going to equal the instantaneous rate of change. And that is only true for lines because lines have constant slope. This little quotient right here has a special name. You'll start to hear me refer to this several times. This formula right here, where we're simply doing change in y over change in x, that is what we're going to be calling the difference quotient. We will come back to this in several different forms and different formulas of how we're going to look at this, but we're essentially going to be continually calculating a difference quotient. All right, now in this next example, what we're going to be looking at is, now, little review, find the slope, still a line. So even though it says at x equal to 3, it really doesn't matter. It could be really at any point because of the constant slope. So part A, let's find the slope. And usually, most of the time, you're probably used to just going ahead, solve for y, get it in the slope-intercept form. Your slope-intercept form is your y equals mx plus b, so I simply need to solve for y. So in our problem, we have 5x minus 3y equals 2. Negative 3y equals negative 5x plus 2, divide by -3. And so we get 5/3 x minus 2/3. And so we know that our slope at x equal to 3 and everywhere else is 5/3. So we could answer that question and it's fairly straightforward. For this next part, it's asking me to find the line's instantaneous rate of change at x equal to -50. Well, remember, slopes are constant on lines. Helps if I could spell correctly there. Slopes are constant for a line. So the slope, or actually let's use the notation that they're actually asking us. The slope, which is the instantaneous rate of change, at x equal to -50 is the same as it was at x equal to 3, and so it is 5/3. Okay? No different. We're on a line. Lines are the easiest thing to look at. We're not even really have to think about calculus here. For part C, it's asking what would be the line's average rate of change. Well, because this is a line, your average rate equals your instantaneous rate. And again, that's only true of lines. I am emphasizing this because we're going to leave lines behind fairly quickly. And since the average rate equals the instantaneous rate, the answer is again 5/3. The next question would be, what would happen if I were to take the line and vertically shift it up or down? So if I'm taking this line, which in our slope-intercept form, just kind of think about this visually, what's going on. So I have -2/3 is my y-intercept, and then I'm going to go up 5 and over 3, and we're just estimating. So I can draw my line in. What would happen if I were to shift that up or down? What would happen to the slope? And hopefully you can very quickly go, nothing would happen to the slope. Vertical shifts, whether you're going up or down, do not affect the slope. And if it doesn't affect the slope, then it doesn't affect the instantaneous rate of change, and it doesn't affect the average rate of change for the function. So if I were to say what would happen to the slopes, the answer is going to be nothing. The slopes are exactly the same whether I shift the graph up or I shift the graph down. Just a kind of important little side note, we'll come back to this in a little bit. So kind of important thing to think about here is that the slope of a line, okay, specifically of a line, that it is a constant slope. That any and all points of the line, no matter where you are, it has the same slope. So an increase of 1 x unit will always correspond to a change of m, the slope, y units. Any and all points, your average rate of change is going to be equal to your instantaneous rate of change. A couple of special linear functions that we want to, or well, lines that we want to look at, not necessarily functions. The slope of a horizontal line, where you have like y equals a constant, is equal to 0, because your change in y is equal to 0. You get 0 over a number. Okay, 0 over number is 0. And then the slope of a vertical line, in a vertical line, your change in x is 0. So you end up with a number divided by 0. And what you had said before probably was that this is undefined. What we really want to say here is that really in this scenario, what we're saying is that your slope is either infinity or negative infinity, that it's impossibly steep, if that's a way to look at it. So an undefined slope either has a slope that is infinity or negative infinity. It's kind of a concept that's going to come back when we start doing this idea of this limiting process. Okay? Now the big question is, what would happen if we tried to change and start looking at the slope of a curve, not a line? Because on a curve, obviously the slope at any given instant is going to be changing over time, just like you saw in the Usain Bolt example. So for example, I'm going to be looking at the function x squared plus 1, nice easy function, nothing more than a parabola that has been shifted up 1. So we'll just do a nice rough sketch of it. So I have my parabola that has been shifted up 1, and I want to talk about the slope of this parabola, and maybe talk about where the slope is negative, or the slope is positive, or the slope is 0. And hopefully you can kind of take a look at this and then have this idea that the slope, this idea of these tangent lines that are kind of touching this curve, that if the function is decreasing, then you have to have a negative slope at every given point. So I would say that the slope is negative for your x values between negative infinity and 0, that your slope is positive for your x values between 0 and infinity, and your slope is 0 at x equal to 0, which would be that where the tangent line kind of comes across, kind of kisses it, and you have a horizontal line. When you're over on this side, your tangent lines will have negative slope coming down. When you're on this side of your parabola, your slopes will be positive or rising. So we have falling, horizontal, and then rising. So if we want to know, well, what can we say about the graph in each case, I'll put this over here right next to it, that the graph is, when the slopes are negative, the graph is decreasing. When the slope is positive, the graph is increasing. And when the slope is 0, notice at this case that you have the graph has an extrema. A place where you have, in this case, it happens to be a local and global min. because it's where the graph has switched increasing to decreasing. Switches increasing to decreasing. And that's going to be something that's going to be important a little bit later, that this idea that if I can find the slope of this tangent line, that wherever the slope is 0, that would be a candidate for a local or global extrema. All right. Now, part C here says, well, what if I wanted to find the slope of the graph at x equal to -3? So maybe this right here is -3, and I want to find the slope particularly at that 1. Well, the problem with that is, and the difficulty is, we only have 1 point. So just like the Usain Bolt example, in order for me to find this slope at -3, I don't have 2 points. So what we're going to have to do here, and kind of the difficulty and what's going to bring calculus in, is this idea that we're going to have to use a limiting process. That what we're going to have to do is we're going to have to pick points close to -3, and we're going to calculate the slopes, we'll say, of secant lines. Secant lines are lines that will intersect the curve in 2 points. And so we'll calculate the slopes of secant lines using points close to -3. And we'll use a limiting process. We'll let the point get closer and closer and closer, and then we'll use that to help us kind of estimate. And this limiting process is what we're bringing in the idea of calculus. All right? So slopes of lines are easy. You can use the difference quotient, change in y over change in x. You need 2 points of a line. When we're on a curve, we only have 1 point, and that is the difficult part of this. And so we want to calculate slope on 2. If we use 2 points, we actually get the average rate of change, and that line is going to be a secant line. And what we really want is the slope of the tangent line, and that's a line that just kisses the graph at the point. And so the idea is we're going to use the secant line slopes, and we're going to use a limiting process, bring in some calculus, and use that to estimate what the tangent line slope is going to be. The slope of the tangent line is our instantaneous rate of change. Slope of the secant line is the average rate of change. So those are going to be 2 big important concepts that we're going to be doing. The average rate of change is a pre-calc or algebra concept, whereas the instantaneous rate of change is going to be a calculus concept where we are going to use a limit in order to find it. Okay? And then just a little history while we're here, that calculus was really discovered independently by 2 different people. And we're going to come back to this because there's a whole drama. It's like a soap opera between Leibniz and Newton. 1674, Leibniz was in Germany, and he was trying to find the slope of the tangent line, kind of what we're doing here, kind of a classic problem. A little earlier, in 1666, Isaac Newton was really trying to determine how fast a particle in motion was moving at a given instant. And it turns out that the answer to these questions are both the same in their calculus. There's going to be a lot that we talk about with Leibniz and Newton. There's kind of a feud that kind of went on who gets credit for being the founding father of calculus, which we'll discuss a little bit more later. All right, so the key idea here is that if we were in pre-calculus, we would be calculating average rates of change and slopes of secant lines. If we are in calculus, we're going to be calculating instantaneous rate of change and slopes of tangent lines. All right, so let's actually show how we're going to use the calculus, how we're going to create this limiting process. So we have our x squared plus 1, and what we want to do is we want to calculate the slope of the secant lines, and we have several points that we're going to be calculating. So we're going to set up a difference quotient for each one and calculate. Now what I want you to notice is that the second point, as I move through here, is getting closer and closer to -3. And that's where the limiting process is going to be in. I am basically going to be finding secant lines, and I'm going to move the points closer and closer and closer to help me estimate the slope of the tangent line. All right, so taking a look at the first example, I mean, this is fairly straightforward. First thing you have to do, because I only gave you the x values, is you need to find the y values. And remember that your points, you would have -3 and f of -3, which basically means plug -3 in and see what you get. You're going to get 10. Your other point would be 5, and then f of 5. Plug your 5 in and you get 26. So we know we're calculating the slope of the secant line by using our difference quotient, our change in y, 26 minus 10, over our change in x, which is 5 minus -3, and we calculate our slope. We're going to end up with 16 over 8, or 2. Okay, so the average rate of change for the slope of the secant line between -3 and 5 is going to be 2. And then I just repeat the process down here. We still have the -3 10, so we can kind of in all three of these cases add that in, -3 10. We find the other point. We're going to move the point just a little bit closer. So we're going to plug in 2 now into our function. So f of 2 is going to be 5. Calculate our slope now. So we would have 5 minus 10 over 2 minus -3. So -5 over 5. So now we're at -1. Calculate it again. We're going to take our point 0, f of 0, which is going to be 1. So our slope, 1 minus 10 over 0 minus -3. -9 over 3, which is -3. And then our last point, -2, f of -2. Plug in -2, we end up with 5. And so now our slope is going to be 5 minus 10 over -2 minus -3. So 5 minus 10, -5 over -2 plus 3, 1, -5. Now let's kind of take a look at what basically is happening here as we are working this problem. I'm just going to pull my calculator out. And I'm going to graph my function, and I'm going to look at these secant lines on the graph. Okay, so through the magic of pausing the video so you don't have to sit and wait while I kind of input all of these items into my calculator, but what I have done is I have taken each of these slopes that we calculated above, and just a little review coming in. I use the point slope form of a line in order to enter them in each of these equations in. So like for the first one, I would have done y equals my slope was 2, and then x plus 3 plus 10 to get the secant line. Okay, and then all I did for each one was simply change the slope. You had a -1, x plus 3 plus 10, your -3, x plus 3 plus 10, and your -5, x plus 3 plus 10. So I entered all of those into my y equals as long as the parabola. And now taking a look at this, what I want you to see is that the yellow line is actually the tangent line. So if I were to zoom in, let's see, let's try 400%, so I can take a closer look at this. So the yellow line that's right here is the tangent line, okay? So let's do this in orange. So that is my tangent line. And then we started calculating the secant line. This was the first secant line I calculated. Here's the second one. Here's the third one. Here's the fourth one that I did. What do you notice about the slopes of these secant lines as I get a point? Notice that my point each time is moving closer and closer on the curve to the point of interest, which of course is my -3, 10 that we're looking at here. So as the points move closer and closer, the secant line is also getting closer and closer and closer to what the tangent line is. So the idea is that when I am taking a look at this, that as the points get closer, as our second x value converges or approaches 3, then the secant line becomes a better and better approximation of our tangent line. So the secant line approximates the tangent line. And if the secant line is approximating the tangent line, the slopes of the secant will approximate the slope of the tangent. And that's the idea of our limiting process, is that if we allow the points to get closer and closer and closer together, then what we're managing to do is to basically come up with an estimate for the slope of the tangent line. Now, however, we're not going to just be happy with just getting an estimate. We really want to be more clever than that and use a limiting process and do some algebra where we can actually calculate what's going on. So here's what we're going to do. We're going to use that difference quotient, change in y over change in x, and we're going to calculate the slope of a secant line, but we're going to use this point, we're going to use the negative 310, which is our point of interest, where we're interested in finding the instantaneous rate of change or the slope of the tangent line. And then I'm going to use as my second point a more generic, some x value that is a small distance away from negative 3. So that's what this little h is referencing. And then, of course, I have to get the y value, and you find the y value by plugging your x value into your function. Okay? So my difference quotient, so part A, the slope of the secant line, also known as average rate of change, we are going to find by doing our change in y over change in x. So y2 minus y1 over x2 minus x1. But more specifically, our y2, because this is our x2 and our y2. So we're going to do f of negative 3 plus h minus f of negative 3. There's my, we'll plug it in a second, but this is my y1 and my x1, all over my negative 3 plus h, my x2, minus my negative 3. So I'm going to do a little algebra now. I'm going to use this slope of the secant line in this generic form, and I'm going to calculate this. Remember that function notation, we plug whatever is in the parentheses in for x. So that's going to give us negative 3 plus h squared plus 1. We're going to subtract your point, y value for negative 3, which was 10, all over negative 3 plus h minus negative 3 actually simplifies down to h. We're going to continue with our simplification. We'll go ahead and FOIL this out. You should be able to do this in your head at this point. 9 minus 6h plus h squared, and this is going to be minus 9, collecting like terms, over h. We have some cancellation going on here. The 9's will go away. I'm going to factor out an h, and I'm also going to write the h squared first. So h times h would give me the h squared minus 6 all over h. And now I'm going to cancel, simplify myself down. So we have this idea some nice things are happening with our simplification, and we end up with h minus 6. So if I know how far away I am, what the distance h is, I can simply plug this in and find the average rate of change. Okay. Now, when I come down here, we've simplified. I want to analyze what happens as h goes to 0. So for B, what we're actually doing is we're going to calculate the slope of the tangent line, which is the instantaneous rate of change. And to do that, we're going to add a limiting process. This is where the calculus comes in. What we did in part A, this is really just pre-calculus. Nothing special, just some plug and chug with the difference quotient. Now we're going to add some calculus in. We're going to add a limiting process. So we're going to do the limit as h goes to 0 of this simplified version, h minus 6. And hopefully this is fairly straightforward to take a look at, that the actual, if h is going to 0, now that I've removed the division by 0 problem, this is what our algebra simplification did for us. We removed division by 0, and that's what was causing the problem. We couldn't just let h equal 0 up here because we would get a division by 0 problem. But once I do a little algebra, I can remove the problem I'm having. These are equivalent except for where h is equal to 0, but when we're doing a limit, the idea is it doesn't really matter that, we'll kind of go back to our pre-calculus, that there was really a point discontinuity at this location, and that if you were looking at the graph of this slope, what's happening to these slopes over time, what you'll basically have is a point that's coming in, has a hole, and then keeps going. And so the idea is if I just want to know what the value is approaching, I don't need to worry about the fact that there's a hole there. I can basically now just put in the 0 and say you're going to get negative 6. Negative 6 is going to be the slope of the tangent line at x equal to negative 3. And I found that by doing a limiting process. Alright, so now we're just going to repeat the process, and we're going to use the limiting process. We're going to kind of take out the two-step part of it. We're going to go straight to finding the instantaneous rate of change using the same function, but we're going to do it at x equal to 2 this time. And so kind of just looking back at our graph that we had on the previous page. So at x equal to 2, that's this point right here. So now I'm going to be looking for this tangent line slope, which of course you can say, oh, that's a positive slope, and that's what we're going to be expecting to see there. So we're going to do it all in one step. We're going to simplify and do the quotient, the difference quotient, everything in one step. So we're going to say the instantaneous rate of change. We're going to make sure we do the limiting process, the limit as h goes to 0 of our f of 2 plus h minus f of 2 all over h, because the 2 plus h minus 2 is always going to simplify to h. We're going to go straight to this part of our difference quotient. And as you can hear the nice mowing yard in the background, getting ready for school. I'm sitting here at school for you guys. We're going to just plug and chug using what we did before. You have to bring, this is kind of a notation thing. One of the things they're pretty big on in the AP is good mathematical communication. And we're indicating that we're going to be doing a limiting process by putting this symbol, the limit as h goes to 0. And you have to write it every single time until you actually apply the limiting process. So we bring it along with us, and now we're just going to do the algebra. We would have our 2 plus h squared plus 1 minus our f of 2, which was 5, all over my h. Bring down to the next line. We'll go ahead and FOIL this out. 4 plus 4h plus h squared minus 4. And again, make sure you write the limit as h goes to 0 in front. Kind of squeeze it in there if you forget. We look for things that will cancel because we're trying to simplify. We see that we have a way to remove the division by 0 problem, because once I get to here, I realize that I can factor out the h, 4 plus h, all over h, and now I can remove the division by 0 problem. I can cancel the h's out, and then here's where I can take the limit. If we're going to now, we're doing the limit, we're going to let h go to 0. Now that I have removed the problem, now I can plug in the 0 and see that I am going to have a value, an instantaneous rate of change, or slope of the tangent line of 4. Now this limit method works pretty well, but you have to set the difference quotient up every single time you want to slope at a different point and go through the process. And then simplify using the algebra. And you really notice that they're very similar in that, the foiling, the canceling, the removing the common factor, that it kind of works out that in this you don't have to keep repeating this several times. We'd like to be more efficient. So what we're going to do is we're now going to find the slope at any point. We're going to keep it generic on the function y equals f of x. So instead of picking 310 or negative 310 or 2, 5, what we're going to do is we're going to leave it as x f of x, and we're going to use that to come up with our difference quotient. So we're going to have this as our first point. So this is going to be our x1 and our y1. And then what we're going to do for our second point, the point that's going to get closer and closer, we're going to do x plus h. Notice that instead of a number here, we actually just leave it generically x, and then f of x plus h. And so what we do for our difference quotient then is our slope of the secant line is going to be your y2 f of x plus h minus your y1 f of x all over your x plus h minus your x. And just like before, this will simplify down to a more generic formula for your slope of your secant line, or your average rate of change, f of x plus h minus f of x all over h. And if your pre-calc teachers and your algebra 2 teachers have done a good job, you have seen this difference quotient before. And you have worked with this difference quotient before, because simply plugging and chugging and finding a slope or an average rate of change that we can do this in a generic formula, and we've worked with this before. If we want to turn this into the slope of the tangent line, or the instantaneous rate of change, and again, this is not at a specific x, but at a generic x, all we have to do is add the limiting process, the limit as h goes to 0, of f of x plus h minus f of x all over h. Now, and then just to be thorough, there will be some textbooks and some notations that will use, instead of h, they would use delta x. So it would say the limit as delta x goes to 0, f of x plus delta x minus f of x all over delta x. They just use delta x instead of putting in the h, which is a common kind of notation that they use. So over here on the next page then, very important idea, the slope of the tangent line is the limit of the slope of the secant line. That's the key idea that's bringing in the calculus. Your 2 points are x f of x and x plus h f of x plus h. And then we can state this mathematically, and notice I'm going to use a new notation. This notation where we have f prime of x, this is actually a function now. That all I have to do, this will give me a formula for the slope of the tangent line at some value x. And so typically we call it the slope function. It's also known as the derivative function, also known as the differential. So this process of calculating the derivative function is what we call differentiation. Another notation, because we talked about that Khan was talking about in the Usain Bolt example, dy dx, or we can just simply write y prime. These are all notations that you would use, and how you calculate this derivative is you do the limiting process on the slopes of the secant lines. All right, so now let's look down here at example 9. Same function. Now we're going to find a generic formula for the derivative, the formula that will give me the slope of any secant line. So we're going to do the limiting process as h goes to 0. We're going to do f of x plus h minus f of x all over h. We will plug and chug, just like h goes to 0. Plug in x plus h, so it's x plus h squared plus 1 minus, now be very careful here, do you see these big parentheses? Whenever you subtract the function, you are going to have to remember that you will need to distribute your negative through. Don't forget to bring your denominator along. Now we continue, we do a little algebra here for our part A. We're going to FOIL, just like you did in the last examples, except now instead of a number here, you have a generic x. So x squared plus 2xh plus h squared. plus 1, distribute your negative, minus x squared minus 1 all over h. You will see that there's some cancellation, just like we had before. Our numbers are going to cancel out. What we're left with, notice I'm bringing the limit each time. I haven't done the limiting process yet. All I'm doing is algebra simplification. I have some more cancellation that I can do. This x squared and minus x squared is going to go away. So notice that what we have left has an h here, and that's h squared, so I have an h there. So of the two items I have left, what I'm going to do now is I'm going to factor out an h, 2x plus h. Then that allows me to remove the division by zero problem. That is why we can't just directly calculate the slope of the tangent line. And we're at the limit as h goes to 0, 2x plus h. And now we're actually going to do the limit. We're going to take the limit. We're going to say as h goes to 0, now that I have removed the division by zero problem in the previous step, I can now just substitute it in and say that when h goes to 0, this formula is going to be 2x. So what this tells me is that a formula on this function, the derivative of x squared plus 1, is going to be found by simply doing twice whatever x value I want the slope at. So when we take a look at part B, where we're calculating f prime of negative 3, now if we look back at what we had done with the work on that, this page, that we calculated it to be using the kind of more specific, letting it be negative 3 in there, negative 6. You can see that when you look at it, when we were doing these, 2, negative 1, negative 3, negative 5, you can see the slopes are approaching negative 6. Now I can calculate it directly. All I have to do is say I want to calculate this, I'm just going to plug it in. 2 times negative 3 is negative 6. If I want to calculate, it says interpret, so this would be the slope of the tangent at x equal to negative 3 is negative 6. And instead of slope of tangent, you could also say the instantaneous rate of change at x equal to negative 3 is negative 6. Notice this is going to be very important. You have to say at what instant when you are doing the slope of the tangent or the instantaneous rate of change. If we were to calculate, we want f prime of 2, which we already know is 4, but we'll go 2 times 2, just verify, we get 4. Slope of the tangent at x equal to 2 is 4, which makes sense. You're on the side where it should be positive. And then we did f prime of 0, and hopefully from the very beginning of this, you should be able to answer that question and remind yourself what was happening at x equal to 0. At x equal to 0, we had an extrema. In the tangent line, at an extrema, where you switch from decreasing to increasing, has a slope of 0. So the slope of the tangent at x equal to 0 is 0. Another way to think of this, if we were actually talking about instantaneous rate of change, your speed, how fast you're going, or really your velocity, okay? Velocity is where you have direction as well as magnitude, positive direction, negative direction, and so on. That what you can say about this function is that your velocity, your instantaneous velocity, instantaneous rate of change at x equal to negative 3 is negative 6. So, which basically means your speed is 6, but in the negative direction because the function was decreasing. The slope of the tangent at 2 is 4, so your instantaneous velocity is a positive 4 because the function was increasing. So you were going at a speed of 4, you were going in the positive direction, or increasing. And then your slope at x equal to 0 is 0 because, well, if I went from decreasing to increasing, my speed's going to have to slow down, come to a stop, 0, and then continue in the other direction. And so that's the idea of where it switched from being in the negative direction to the positive direction. and it switches, you must have a speed of 0 or velocity of 0. All right, example 10 goes back to a previous example. What would happen to the derivative function or the specific slopes we calculated above if I simply shift the graph up or down? If I take my y equals x squared plus 1 and I shift it down to here, and I look at my slope at -3, and I look at my slope at -3, you'll see that those are still parallel. They have the same slopes. Vertical shifts do not change the slope at a point because your change in y is still the same because you moved both of your y values down, okay? And so is this result true? What happens? The answer is nothing. They are the same. And is this result true for all functions? The answer is yes. Shifting up or down does not change how fast the function is changing at any given time. Just a little notation here at the bottom to remind you, your derivative is a function. It's going to give you the slope of the tangent line of the function at a particular point, at an instant. That's going to be the key here. And you will always have to reference what instant you are looking at, and it's also the instantaneous rate of change or instantaneous velocity of the function. The notations, f prime of x, y prime, and dy dx. Also the differential of y with respect to the differential of x, the derivative of y with respect to x. All of those mean the same thing, and we're talking about this derivative function. And that will be the end of our introduction to derivatives, which what you'll see is in chapter 2, for the rest of chapter 2, we're going to busy ourselves with how do we calculate limits, because it's not always going to be as straightforward and easy as calculating the limits that we have here, because this was a fairly simple function, x squared plus 1. So we're going to spend most of chapter 2 talking about the limiting process and how do we calculate limits before we get into actually using the derivative and finding some applications for it.